Okay, it often happens that we want to find the components of a vector parallel and perpendicular to another vector. What's that mean? Well, let's just see what happens when we project V on W, and then we'll come back to that question. Okay, so here's the line defined by W, and of course I got V and W emerging from the same initial point. I can project V onto the line of W, and I can then draw the projection. And we know from what we've just done that this projection is easy to calculate if we know the components of V and the components of W. So we get the projection onto W of the vector V, and we know that there's a mathematical expression, an algebraic expression that we can use to actually calculate this very easily. Now, what about a component of, so we would say that this projection is the component of V in the direction of or parallel to W. Okay? Another component would be this vector here. Component means if you add the components, you get the thing. Okay, if you add the components of V, then you should get V. Well, clearly this vector plus this vector gives you V. And since your projection line is at a right angle to the direction of W, with the projection of V onto W being along that line, we see that these two vectors are parallel. So we're going to call this V perpendicular. So that V can be expressed in components I'll use the word orthogonal. Means the same thing as perpendicular when you're in a Euclidean space. V can be expressed in orthogonal components as V parallel equals the projection of V on W and V perpendicular or orthogonal. And what does V perpendicular equal? Well, there is V perpendicular. This is now what we want to call V parallel, the part of V that's parallel to W. What about V perpendicular? Well, V parallel plus V perpendicular equals V. Okay, so over here we can say, now that we said V parallel is this projection, then V equals V parallel plus V perpendicular. So V perpendicular must equal what? Now this is an equation now by the rules for vector spaces and so forth, and just from understanding vectors in any way, we understand that we can do addition and subtraction and multiplication of vectors by constant numbers with impunity. That is, we can do algebra with vectors just the way we do it with numbers, for symbols representing numbers, as long as we don't get into multiplication, because multiplication of two vectors is not defined. So using what we know, we see then that V perpendicular, or V, the orthogonal component of V, is V minus V parallel. Okay, so V perpendicular is just V minus V parallel. Now, of course, if we want to calculate these things, we calculate them using dot products and magnitudes. So we could say then that V parallel equals the projection onto W of V. And this board's a little wobbly there. Okay. And remember that that equals V dot W over the magnitude of W, which gives you this distance and also tells you whether this distance is in the direction of W or opposite the direction of W. So if the dot product is positive, we'll have this distance in the direction of W. If the dot product is negative, we would have this same distance but in the direction opposite to W. Okay, so anyhow, there's V parallel is this multiplied by just the unit vector in the direction of W. So that V perpendicular equals V minus V parallel, but of course that then equals V minus V dot W over magnitude of W multiplied by W over the magnitude of W. Now you don't remember this as a formula. You might decide to remember this as a formula because it depends on how good you are at deriving things. It's a direct consequence of the definition of the dot product. But what you remember is this picture. We know we have a formula if we need to use one, or at least a mathematical expression that we can write down with understanding, we hope, to calculate this thing. And if we subtract this thing from V, we get this thing. Okay? There's the picture. There's the idea. And now we have a way of getting components of V, vectors that add up to V, not only components but perpendicular components that add up to V, with one component in the direction we choose, the direction of W.